And for our second lecture for characteristic classes, last time I gave a sort of conceptual sense for characteristic classes as measuring vector bundles by taking vector bundles, restricting them to cycles, and giving you numbers. The example being an Euler class that you can then, so an Euler kind of count. So today we're going to talk about broader constructions, which will be useful, especially as we develop the theory. But it's, you know, a relatively useless category. So that's what vector bundles form. So what is that category? Well, if I have two vector bundles, let's remember we've got, again, by abuse, I might call them E and F, say, or maybe E prime, because F is sometimes fiber, over two base spaces X and Y. Well, there's some map from E to E prime, so that if I call this pi E and pi E prime, and then pi E, the preimage of a point is V, and pi E prime, the preimage of a point is W, then what I want is that if I F restricted to V, which again is by abuse, there's lots of V's, but I take any preimage of X, which is isomorphic to V, and restrict it to restrict F to that fiber. So then, oh, and that's not F, that's, well, let's call that capital F. Or maybe even phi. Sorry, you prepare sometimes and you realize, oh wait, what is the best choice of letter? So if I restrict to a fiber, and over here, of course, you're mapping to F of X, and so that's W, then I want this composite to be linear. Because of course the linear structure is what we emphasized in the basic definition. So so it's pretty immediate that these will compose, linear maps compose, and continuous maps compose, and if this diagram commutes, then the diagram with X to Y to Z will commute. So it is a category, that's fine. I'll say why I'm denigrating it in a bit, but just generally categories, it's kind of like groups, right? Well, groups are great, but you know, we often want things like vector spaces, modules over a ring, or some other structure on a group to make it a much more useful class of groups. And same with categories, you want some good limits and co-limits, you want some symmetrical monoidal structure, and abelian category. There's all sorts of categories that really capture things that that are more helpful. So anyways, but let's give a couple examples. One I won't go through very much, but I mentioned it last time. If I've got a vector bundle, and then I've got a subspace, then I can take, again, if this is pi, the preimage of that subspace will be another vector bundle, and then this is a map of vector bundles. So there's a couple things to check, but it's a fairly immediate exercise that this is a vector bundle, and then this would be an example of a morphism of vector bundles. Another example, much more interesting to me. Suppose I have a non-zero section, so that means non-zero everywhere. So over every x, the image of sigma is not zero. Then I claim there's a morphism you can consider, a new line bundle, namely, let's call it E sub sigma. What it's going to do is be a line bundle. So let's call the fiber vector space L. And what is L? It's going to be the span of, so L, which again should be this, call it pi sigma, the preimage of some x, is going to be the span of sigma of x, which remember is just a vector in V, so its span is a one-dimensional subspace. And then this becomes a morphism of vector bundles. More generally, so there's a couple things to check there, but again, I'll let that I'll let that sort of be a standing kind of exercise. More generally, if we take V of rank n, that just means the dimension, and I've got n different sections, then, well, I've got the trivial bundle, and then I've got my original bundle. And what we can do is I claim to find a morphism by sending x cross some vector, call it a1 through an, to the sum in that fiber. So every fiber has a good linear structure. So one thing we can do is sum things in the fiber of ai times the ith section. And if these are, I should have said, these are all linearly independent over each x, i.e. sigma 1 x, sigma n x inside of V are independent for any x. So it's a very strong assumption. We saw that some bundles, there isn't even a sigma 1. There is not a section, so that the section is independent for all x, because if I have a single vector which is 0, that is a linearly dependent set, of course. In any case, this is an example of a morphism of vector bundles, and what one can do is show. So proposition, this is theorem 2.2 of Milner and Stasheff, is that this this map, this morphism, is invertible, is an isomorphism. The morphism I just constructed there. So there isn't too much to it. It's obviously one-to-one, pretty clearly onto. You would want still the standard thing topology, some continuity of the inverse map, but that's not too hard to establish. So I won't say too much about that. That is in Milner and Stasheff's book. So what this says is that any rank in bundle with in sections is trivial. In particular, any line bundle with a section is trivial. So let me, just any line bundle with a section. So let me give you an example. The twice twisted Mobius bundle. And let me put that in quotes because we're going to see that depending on the category and the category we're dealing with, I claim that this is trivial. So what could I mean by the twice twisted Mobius bundle? I could mean that, so I've got a strip and I identify, let me use colors, this red with this red, whereas this black is going to that black. But then I also have a third bit where this red gets identified with this black, right? So I'm twisting around twice. And I'm, well, sorry. Sorry, I would have to, what do I want to say? Twice twisted. I mean, let me say that again. In 3 space, it would look like this. Trying to say this in topology with identifications though. So we have a sense for what that is. Of course, it's a vector bundle. So really each of these is a copy of the real numbers, but I'm just using the disk, what's called the disk bundle in the vector bundle to be able to picture out what's going on. Right, so really I would mean that I'm going to make a bundle over the circle by quote unquote twisting twice. That means that that first, well, yeah, it becomes it's a good question about how to explain what this is as an abstract vector bundle. But the point is that it is trivial, even in this model in R3, the 0 section is running along the middle. And if one follows around, you can make, I'll put it in purple, I claim a non-zero section that misses everywhere and comes around and is non-zero. So the idea is that, well, here would be a perfectly good section that even if I think of this as twice twisted, it's still a non-zero section. And it realizes this as trivial. The key is that, so these are isomorphic vector bundles. So twice twisted Mobius and the trivial bundle are isomorphic, but this embedding in R3, really an immersion. If we think of the whole bundle, the points as those green lines are going to intersect this shape again. But this immersion in R3, or the embedding of just the disk bundle, is not isotopic to the standard, a standard embedding of the annulus, or again, immersion if I'm thinking of the whole bundle. So that's that sometimes confuses folks, but it's hardly any different than the fact that like the trefoil knot is actually homeomorphic to the circle still, but it just doesn't look like the circle because we, if we're thinking of it as in R3, we want to think of a different kind of equivalence relation, namely isotopy. Okay, so so let's talk a little bit more about the structure of this category of vector bundles. And you really want to think about it as having both, well, it sort of inherits from both vector spaces and topological spaces. And so, so there's some interesting structure coming from both what we know about vector spaces and what we know about spaces. So I've decided to pick on the vector spaces first. And so, so let's just talk about that additional structure. I think the appropriate name is the structure of some endo-functors on this category of all vector bundles. I'll call it vect over top because if you fix a single base, it's traditional to call that vect over x or just vect parentheses x. So I'll call this vect over top because these are fairly universal. So there's some additional structure coming from that. Some of the known structure vect. In this known structure on vect, there's kind of two schools, so to speak. Representation theorists like endo-functors, that's key if you're, say, studying representations of symmetric groups and general linear groups and all. I mean, general linear groups is almost by definition endo-functors, and then there's this beautiful classical and even, you know, currently generalized theory of representations of symmetric groups, which rely on those functors from vector spaces to vector spaces. But a lot of folks, algebraic geometers, algebraic topologists for that matter, like to play with things like exact sequences of vector spaces. And I'll say that I'll explain in a little bit that game doesn't work as well. So let's give some of the first examples. First as in technically least difficult examples. So if I have E over X and E prime over Y, then I can take the product and you see that you get the product of finite dimensional vector spaces, but that looks like then the direct sum over the preimage of a point. So again, consider a little exercise to say that this is a vector bundle. But then from our previous example, and so this is what you might call an external direct product. So then for the internal, you can restrict E plus E prime over, if I've got X cross X, to the diagonal copy of X, and you get something which, well, you know, again, maybe I want to call this E cross E prime for external, but yeah, there's no, it's usually pretty clear. One is a vector bundle over X, one is a vector bundle over X cross X. And so I often use direct sum for both. So that's the simplest thing you can do. You can take a vector bundle and take its direct sum with another vector bundle over the same base using this little trick with a diagonal function. But really, let's think about what how would we really see this as a vector bundle then from our definitions, or how could we verify this as a vector bundle from definitions rather than sort of two separate constructions? Well, we see that if U is an open neighborhood over which E is trivial, and V for E prime, then over their intersection, they're both trivial. And what we can do is, of course, still cover X by intersections of such U and V. If I've got two different covers, their intersections still cover. And so so I've got these trivializations, and then what I can do is, so over U intersect V, we can take, again, just call it the external direct sum of the trivializations, trivialized restrictions. That's fine. That's going to be a nice trivial bundle. And then we had these transition maps. So now, then, what you have to do is take the transition maps and take their direct sum. By which I mean, so if I have U intersect V overlapping with U prime intersect V prime, then I had some linear map. So over, I had some linear map for every point in U intersect U prime, which was sort of a phi, let me call it phi sub E, which is a linear map giving an isomorphism between the two possible trivializations of E over the point X in U intersect U prime. And similarly, I have a phi sub E prime over V intersect V prime. And the direct sum of two linear maps is another linear map. And so that's what's giving these trivializations, that's what's giving the overlaps between these trivializations. And so what you realize is that any continuous functor, there's a little bit to check, because the point is this direct sum then these isomorphisms are continuous in the variable X, and so we need that to continue. If I've got two continuous families of matrices, then their direct sum will also be a continuous family of matrices. So the upshot is that any continuous let's go back. So in general, any continuous functor of vector spaces gives rise to an endo-functor of vector bundles over a fixed base space. So just the subcategory of this big useless category vect over top, namely vect over X. you can think of this then as a functor on vector over top, but it's really just, it's never changing the base spaces. So we often think of those subcategories, fix a base space and just consider vector bundles over X. So examples are tensor product, direct sum n times, if you will, tensor product n times, exterior powers, homomorphisms. So that's, you know, and then composites of these. And as Milner and Sasheff note, and is key, these are critical in differential geometry. So various tensors, the curvature tensor. If you do Durham theory, you're really looking at taking the tangent bundle, taking the linear dual, and then exterior powers on that. So so you don't have to use this language to do Durham theory, but Durham theory very much fits in into this. I don't think there's a lot I want to say in terms of the proof that you've got this endo-functor gives rise to an endo-functor, except, you know, it really is that you can trivialize, and then if you're endo-functor, then passes to maps, but that is supposed to be a functor. In other words, if I can take the direct sum of linear maps, if I can take the tensor product of linear maps, if I can take the, you know, Hom induced sort of effect on Hom of linear maps, then and it's continuous, then this gives me a way to take my gluing data, because that's the way I like to think about vector bundles. So here, let me just give my schematic of this. So the vector bundle, the very key thing is that you've got U and V are open sets, and different ways, let me do different colors, different ways to think about trivialization. And then over this blue, for every point in blue, I've got a map. In this case, it would be from black into purple. And if this is the data that makes E, and it very much is the data which determines E. Again, Steenrod's treatment of principal vector bundles very much takes this point of view if you want to do an alternate treatment. Then, if I have some functor, then over U and V as well, and again, this will be just, you know, maybe E plus E itself, because then I have the trivializations living over the same open sets, whereas something like E plus F for two different vector bundles over X is a slightly different matter. But for the schematic, let's just think that I've got the same sets of open sets for trivialization. So you can always take a common refinement. Let me just say that. And then I've got some functor on E, and then I take the same functor on E prime. Then, as long as my phi's, these are my phi's, I can take F of phi as the gluing data for this functor on E. So let me give a few exercises now, or I'm about ready to wrap up. And although I do want to make one discussion, so of what's wrong with this category that we're setting up. We've got these lovely endo-functors, which is great if you're a representation theorist, but if you are more algebraic geometry or homologically algebra minded, you're going to be upset in a moment. Sorry, spoiler alert, or I guess I should call it a trigger warning or something like that. So here's some exercises So let mu be the Mobius bundle for all of these. Then what is mu plus mu isomorphic to? Can you find some, this is going to be a rank 2 bundle over the circle. Is it isomorphic to, well, I guess we can only name one, the trivial bundle. Is it isomorphic to that or not? And then how about mu tensor mu? Same question. What is, can you find that? Now there's 2 line bundles that we can think of. It could be isomorphic to mu, or it could be isomorphic to, sometimes we call it trivial bundle tau. So those are 2 possibilities, or neither. So I'll leave it open-ended. You may or may not have a lot of experience with exterior powers. So part of this is look up exterior power, and can you take the exterior power on the tangent bundle of S2? Now the exterior power on a 2-dimensional vector space will be rank 1. So this is some line bundle on the 2-sphere. It's similar. Take the exterior square on the tangent bundle of the Mobius strip. The Mobius strip is a surface with boundary, a single circle boundary. It has a tangent bundle, and let's play the same game there. And then finally, let me ask the following question, which is kind of related to the next thing that I want to talk about before finishing. Namely, it does, so prove or disprove, that E plus F, say isomorphic to E prime plus F for some vector bundles, implies E is isomorphic to E prime. Great. And then finally, I wanted to say that let's just talk about the deficiency, one of the main deficiencies of vect over top. So vect over top is not an abelian category. That means it's not a good place to do homological algebra. I mean, homological algebra of classical vector spaces isn't that interesting. So you might say, well, that's maybe not that big a loss, but you would think that it should be very interesting in this case. But the one I gave isn't. So, you know, you would need kernels and co-kernels. So probably easier to say co-kernels, of course, so won't exist if one of the main, you know, so here's a first issue, is that the images of our morphisms don't have necessarily uniform rank. So if I try to take a quotient, and we haven't talked about quotients yet, I guess that you could think of that as part of the functors that I've given, but notice I didn't talk about quotient. I just talked about tensor, Hom, etc. So what's a good example there? The standard example is vector bundle just over 0, 1 cross R, trivial bundle, which sends S comma V to S comma SV. So it's got rank, you know, it's sort of schematically, I think of it like this. It's multiplication by some small number. Of course, the image would be the whole fiber, and that's the issue. The image for any S bigger than 0 would be the whole fiber, unless here, 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 and here, it's just that that isomorphism changes. sort of grows as it goes along, but there's a discontinuity and the image there is just 0. So, so that's not good. And let me just say some perspective on this. Oh, and let me actually, let's see, I thought I had, let me copy a Math Overflow posting about this. It's one of the early ones because it's a question that I had myself and didn't get as far on my own when I was younger as this Math Overflow discussion did. Shoot, where is that tab? Oh, there it is. So let me copy it. And let me just go ahead and put it in. It's small, but hopefully, well, you have the link to the whiteboard, or I can, okay. Oh, you don't see it yet. There it is. I'll make that bigger later. So some perspective is that one way to think about vector bundles. So let gamma x be or gamma e, and again by abuse we'll not name every piece of data in the vector bundle, be the sections of then what you have is that this is a module over the ring of functions on X. Now the ring of functions is infinite dimensional, right? So it's not the kind of ring that you learn about when you first do more advanced algebra, 600 algebra at the University of Oregon. But still, it's a ring, and this sort of tells you that you can think of a vector bundle as associated to some module over a ring. But then you actually get that that such are the that if X is compact Hausdorff, such modules are exactly the projective modules. So that would tell you that you wouldn't expect, I mean, just as it's far from the case that every morphism of projective modules has projective kernel and co-kernel, you wouldn't expect such morphisms to produce vector bundles. This is part of the reason that people quickly jump into sheaves once they want to think about this kind of geometry more algebraically. So algebraic geometry really is a place for contemplating these kinds of questions. So that said, let me give so again, you wouldn't expect, so that implies that you wouldn't expect vector bundles as closed under taking kernel and co-kernel of morphisms, because there are very few rings, namely fields, for which quotients and kernels of projective morphisms between projective objects are themselves projective, right? That's just not what you'd expect. I do have a another exercise to contemplate. So in that Math Overflow thread, someone suggested, and I'd always wondered about this, taking constant rank. So if we, well, let me say first. So what happens if you restrict to constant rank morphisms, ones for which the image of the fiber over any point is of the same dimension? Again, this is not even a category. I hadn't seen the example on Math Overflow before doing my prep for today's lecture, but that's kind of fun. It's though over non-compact, so let me call it exercise question. What about constant rank morphisms over compact base spaces? Do those form a category? And if so, is it abelian? This will be a nice little discussion to ponder. Great, I think that's plenty to think about. I think I've taken up a good amount of time, food for thought. So we'll have discussion with my Oregon students soon. And if you're otherwise watching, I hope you enjoy pondering some of these things as well. Let me stop my sharing.